Okay, and for continuing with what we have in working with equations. Now we've been working with combining like terms and working with fractions as well as factoring expressions. And we've been looking at once again factoring expressions, combining expressions, and we've just gone into solving equations. And now for what we have on page 68, we have for number 24, okay, we were looking at this equation in terms of the variable n, and we're looking at not only trying to solve for n, but looking at whether this equation is going to be a sample of a conditional, a contradiction, or an identity. And for what we have in this problem, okay, so we have on the left-hand side, we have 4 times the quantity of 3 minus 5n, followed by the addition of 1 is equal to negative 4n minus 8 minus 16n. And in following through, if I go ahead and distribute 4 over what we have in parentheses, so we're going to have 12 minus 20n plus 1. And to the right, I can go ahead and combine the variable terms. So we have negative 4n and negative 16n, which will combine to negative 20n minus 8. And we have on the left, we have constants to join together. So we have 12 plus 1 is 13. So you have 13 minus 20n is equal to negative 20n minus 8. And for what we have at this stage, okay, there are like terms on opposite sides of the equation. Okay, here we have 2 variable terms and 2 constants, okay, that are separated from one another. And if we look at joining the variable terms, okay, combining what we have in the letter n, and if we join by adding 20n, okay, we're going to have cancellation of the variable terms. And what will be left standing will be constants that will be said to equal each other when in fact they are not. Okay, and so this is a false statement. And for what we have in the letter n, well, the variable terms are canceled out, and there's nothing to rectify the situation. So that means that since there is no logical solution for n, okay, and in terms of performing the algebra correctly, okay, we're down to a false statement. So there is no solution. And the category to which this equation is going to fall under is a contradiction. Okay. Now for what we have in the case of number 26, and we have for this equation, okay, so we're going from the letter n to the letter x, whereupon we have negative 5 plus 3x is equal to 3 times the quantity of x minus 1, followed by the subtraction of 2. And now we have, on the left-hand side, we have just unlike terms, and there's no activity to perform yet on this end of the equation. But now for what we have on the right, okay, we have parentheses to remove, so we have the distribution of 3 over the difference between x and 1. So we have 3x minus 3, and we have followed by the subtraction of 2. So now we have negative 5 plus 3x is equal to 3x, and negative 3 minus 2, so this will become negative 5 And once again, we have two sets of like terms on opposite sides of the equation. And so for what we have now, if I once again combine the variable terms just like what I did with negative and positive 20 in terms of the operation, so we're going to have taking 3x and subtracting. Okay, so you have 3x and negative 3x. So we're going to have the variable terms to completely cancel out. And now we have, once again, we have numbers that remain, okay, and they are said to be equal to each other. And here, like what we had in number 24, okay, we do have a true statement for negative 5 is equal to itself. And so that means that regardless of what you plug in for x, okay, whether it's 0, a positive, or negative, whatever you plug in for x, you're going to end up with the same results on both sides. So that means that you can plug any real value in for x. So we have for this solution, we're going to have a set of all real numbers. And you can symbolize this by the letter R, or in terms of interval notation, you're looking at everything between negative and positive infinity. And in this particular instance, alright, so now when we had no solution, we had a contradiction, but now for the solution to be the set of all real numbers, okay, this one is going to be an identity. Now for what we have in the case of number 28, and this is one that we can work on in various ways. And here we're working with fractional coefficients. Now we have 2/3 of y minus 5 is equal to 1/6 of y minus 4. Now you could combine the y terms and keep the fractions and then just deal with the fractions later. And since we're dealing with an equation, you can also just go ahead and undo the fractions, just multiplying all the terms out by the least common denominator. And the denominators we have are 3 and 6. And 6 is already the least common denominator, for 6 will go into itself, and 3 will also go into 6. And so the least common denominator, that is equal to 6. And if I were to take both sides of the equation, or in this case all 4 terms, and multiply by 6, so you have 6 times 2/3 of y, and we have minus 6 times 5. And we have equal to 6 times 1/6 of y. And we have minus 6 times 4. So we have in the setup, now you can cross multiply, say we have 3 will go into 6 2 times, and 2 times 2y is going to be 4y. But you could also do the gradual reduction. Okay, so you have, think of like 6/1 times 2/3, which would be 12/3 of y. Then we have minus 30, and 6 times 1/6 of y, and so we have 6/6 of y. But again, in cross multiplying terms, 6 will go into itself 1 times 1y comes out to y. So you can use the cross multiplying pathway. You'll still get the same terms regardless. Okay, so you have 4y minus 30 is equal to y minus 24. Okay, now we again have 2 sets of like terms on opposite sides. And the difference this time around is that we don't have the same weights in the coefficients for the variable terms. So instead of like both for y or both at y, we have for y and y separately. And if we look at combining variable terms, say first of all, okay, I generally like to take out the smaller variable term where I can, and that in the long run prevents me from having to work with negatives, especially multiplying or dividing by negatives any more than I absolutely have to. Okay, so if I were to take y away from both sides, so we're going to have 4y minus y, so this will become 3y minus 30 is equal to negative 24. And so here we have in the setup, okay, we have a two-step linear equation. So if I this time around isolate the 3y, so adding 30 to both sides, so we're going to have 3y is equal to 6 and it's by then you can just go ahead and write out the solution. We're going to undo the presence of the coefficient 3 by division, and so we end up with 3y over 3 to reduce to y, and 6/3 is equal to 2. And so for what we will have in effect, just going back to again the original equation, and 2/3 of y minus 5 is equal to 1/6 of y minus 4, and that will ring true on the condition that y is equal to 2. Okay, and so this type of equation will be a conditional. Now, in the crossover, okay, to working with quadratic equations, and for what we have in the mix, okay, we have for number 30, okay, and instead of working with the letter x, like in the examples from the other day, we now have this equation in terms of y. So we have y squared is equal to 18 minus 7y. And if we arrange the terms such that we have the quadratic equation in standard form, in other words, set this equation to 0 and with the y terms and the non-negligible constant arranged in descending degree order. So I got y squared right now by itself, but I combine with the first order variable term by adding 7y and also by taking 18 away from both sides. So we have in the arrangement, we're going to have y squared plus 7y minus 18 is equal to 0. And for y squared, okay, plus 7y minus 18, okay, now we have a factorable trinomial expression. Now for y squared, we can factor this to y and y. And for factors of negative 18, whose sum or difference will end up on the plus side with the middle coefficient 7, okay, and because we have a positive 7, this will signal that more weight will be given to the adding than to the subtracting. So we have for those two numbers of going to negative 18, we're going to have a plus 9 and a minus 2. And in terms of solving for y, again, this trinomial is equal to 0 as long as we have the factors laid out also equal to 0. So if we set first of all y plus 9 equal to 0, we're going to have that y is equal to negative 9. And if we had that y minus 2 is equal to 0, we're going to have that y is equal to 2. And you can go back and check. Now we have the square of negative 9 would be negative 9 times negative 9, which would be positive 81. Okay, so left-hand side amounts to 81. And at the right-hand side of this original equation is the same. We can test this out. We have with y at negative 9, you have negative 7y translates to negative 7 times negative 9, which would be a positive 63, and 18 plus 63 is also 81. And we have with y equal to 2. Now 2 squared is 4. So left-hand side of the equation is 4. And for y at 2, we have negative 7 times 2 is negative 14. 18 minus 14 is also at 4. So y has two solutions with negative 9 and positive 2. Okay, now for what we have, say in the case of number 34, so we have another change up in the variable. This time we're going from y to z. And here we have z squared is equal to 25z. And just want to mention, okay, there might be a temptation to make a careless mistake. And I've seen this before where we've got, z terms on both sides, and I've seen some make the mistake of dividing both sides by z and say, oh, z is equal to 25. Well, 25 is one of the solutions, but I want to mention you don't want to divide too soon. Okay, if you divide by anything, let it be a constant, but not anything in the variable we're solving for. And if you notice, you have that z squared, and that 2 means that you could have possibly two solutions. Not always, but possibly two solutions. Okay, that one, okay, it wasn't asking whether it was any one of the three categories, but this would be a case of this equation would be true on the condition that y be equal to negative 9 or positive 2. So you have a finite number of solutions with only two solutions, and that would have been a conditional. And in fact, I think just about everything else from here on out is going to be conditional. In other words, like if it has like a limited number of solutions, it's going to be a conditional. And if it turns out that the solution is all real numbers, it's going to be an identity. And if there is no solution, like you can't get both sides to work out and be equal to each other, it's going to be a contradiction. Yeah, so everything that we have from here on out, those are going to be variations of conditionals. Okay, and so this equation is going to be true on the condition that y has to be either negative 9 or positive 2. Okay. All right. And for what we have in the case of, you're welcome. Okay, so what we have in 34, okay, so we have z squared is equal to 25z. And here we have a quadratic equation in the letter z. And if we go ahead and write this out in standard form, okay, so we're going to have in this one case, you have z squared minus 25z, okay, is equal to 0. Okay, now it looks like a difference of squares, and it would be if I had just z squared minus 25. But since we have z common, or at least 1 degree z in z common to both terms, we have z times the quantity of z minus 25 is equal to 0, and utilizing the zero product property, okay, so you have the first factor is at z, And if I set equal to 0, okay, so I have that z is equal to 0. And for what we have in the case of z minus 25, and if I set equal to 0, adding 25 to both sides, okay, so we're going to have z is equal to 25. And you can check just the consistency. So 0 is equal to 0, 0 squared is 0, and 25 times 0 is 0. And 25 squared is the same as 25 times 25. All right, and now for what we have in the next portion, and this one, it's going to have a feel of a situation where things are tangled up. And in 35, now we have an equation in the variable m, whereupon we have the quantity of m plus 4 times that of m minus 5 is equal to negative 8. Right. And there might be the temptation to set m plus 4 and m minus 5 equal to negative 8, but you do not do that. And reason for this is that this part here, the constant negative 8, that must be 0 to use the zero product property. So what this means is that if we had the zero product property, we're going to have to redo what we have in the letter m. Okay, so that means we're going to have to untangle the m plus 4 and the m minus 5 by foiling out the terms and then moving the negative 8 over by adding 8. And so just taking the FOIL, we have m times m. Okay, so you have m squared. And then we have with the middle terms, we have outside product is going to be negative 5m. Inside product is going to be a positive 4m. 4 times negative 5 is negative 20. And we have is equal to negative 8. Okay, so for what we have in this particular case, right, so I can move the negative 8 over by adding. And also in advance we have like terms in first order of m. So we're going to have the trinomial m squared minus m. And we have negative 20 plus 8, which will be negative 12. And now we have is equal to 0. And for the factors, okay, m squared goes to m times m. Factors of negative 12 that will have a sum or difference of negative 1, as indicated by negative m. We're going to have more weight given to the subtraction than to the addition. Okay, so this time to use the zero product property from this setup, instead of m plus 4 and m minus 5, we're going to have the binomials to be m plus 3 and m minus 4. And just taking what we have with the zero product property. So if I set the factors to 0, if m plus 3 is 0, we have that m is equal to negative 3. And if m minus 4 is equal to 0, okay, we have that m is equal to 4. And you can just sort of go back and check. So we have with m at negative 3, have negative 3 plus 4 is 1. Negative 3 minus 5 is negative 8. And 1 times negative 8 is equal to negative 8. And with 4, 4 plus 4 is 8. 4 minus 5 is negative 1. And 8 times negative 1 is minus 8. Okay, so And so this is yet another conditional, okay, where this equation is true if m is -3 or 4. Now, we have with the next set of items, okay, this is going to involve what is referred to as the square root property of equality, and just give you a bit of an introduction to this property. Okay, and this property states that if you have the square of an expression and it is set equal to a value, like in this case, if x squared is equal to p, then you have for x, as we go from x squared to x. Okay, so if x squared is equal to p, then we have that x is equal to plus or minus the square root of p. And if we separate the solution, so we have the square root of p as well as the negative of the square root of p. And just taking as examples, say if you're looking at solving for x by SRP, square root property, and we'll say in this one, we'll say that we have x squared is equal to 49. Okay, so we have x squared is equal to 49. Okay, now we have with this one, for x squared equal to 49, so you have x squared set up, p is represented by 49. If I transition from x squared to x, where we're going to have plus or minus the square root of p to become plus or minus the square root of 49. And so for the solutions in x, now the compact notation is plus or minus 7. And itemizing, so we're going to have 7 and -7. So both squares of 7 and -7 will equal 49. Okay. Now let's say if we have x to be represented by a binomial. And so let me change this. I don't want too many 2's here. Let's say we have x minus 4 squared is equal to 100. Okay. So here we have x represented by x minus 4. So if I were to go from the square of x minus 4 to just plain x minus 4, again, so x and x squared is represented by x minus 4, and p is represented by 100. So if we go from second to first order in x minus 4, that is equal to plus or minus, okay, the square root of 100. So you have x minus 4 is equal to plus or minus 10. And again, we're looking at solving for x. And looking at solving for x, okay, so we have, say at the lower extreme, we have x minus 4 is equal to -10. And the other possible value of x will come from the upper end, whereupon we have x minus 4 is equal to positive 10. And if I solve for x, upon adding 4, to both sides of the equation. So we're going to have for x have negative 10 plus 4 is negative 6. And again, you can check for consistency. Negative 6 minus 4 is a negative 10. And the square of negative 10, or negative 10 times negative 10, comes out to 100. Now for x minus 4 equal to 10, again, if I add 4 to both sides, we're going to have that x is equal to 14. And we have 14 minus 4 is 10. And 10 squared is equal to 100. Now there are those quadratic equations that will come out nicely where the solutions will be integers. But you might have those solutions that might not consist of integers or even rational numbers for that matter. And let's say that if I have something like x plus 1 squared is equal to 37. So the square of x plus 1 is equal to 37. And just like what I've done earlier, okay, like with x squared in the first example and the square of x minus 4, I have the square of x plus 1, so I'm going to drop this from second to first order. So you have x plus 1, so take out the 2. And p is represented by 37, so we have plus or minus, okay, the square root of 37. Now, with what we had before, 49 was a perfect square number, 100 also a perfect square number, but for 37, okay, 37 is a prime number, and there's no number times itself among the integers that will multiply into 37 by itself. And so for what we have in this layout, okay, we have x plus 1, again, is equal to plus or minus, okay, the square root of 37. And again, I'm solving for x. And what I'm going to do here is I'm going to take what I have for x and take away 1 and kind of create a little bit of space here. And in the compact solution, once I isolate the variable, I want the plus or minus square root of the irrational number to come at the very end. And what I mean by this, okay, so I have x plus 1, and to undo the presence of the additional 1, I'm going to apply the subtraction of 1, and I'm going to do likewise here, but I'm going to have, instead of plus or minus square root of 37 minus 1, I'm going to put the negative 1 in front of the radical combination. So we're going to have for x, now for the compact notation, we have negative 1 plus or minus the square root of 37. And in terms of what Alex would require, I think throughout Alex asks for just the separate solutions. And so we have at the upper end, okay, we have negative 1 plus the square root of 37. And we have at the lower end, okay, we're going to have negative 1 minus the square root of 37. Okay, so those would be the exact results. Okay, and if you had like decimals, like square root of 37 is like 6 point something, a little bit higher than 6, so you're like negative 1 plus 6 point something and negative 1 minus 6.7. You would have like just a number on the upper end a little bit above 5, and at the lower end you have a negative value that would be like negative 7 point something. Okay. Now, let me mention this. Now, there is another kind of irrational root. And I'm just going to go back to x squared in the setup. Say we're looking at solving for x, and we'll say that we have x squared is equal to And we say that we have 48. Okay, we have x squared is equal to 48. And if I go from x squared to x, I'm going to have the x is equal to plus or minus the square root of 48. Okay, now I know like in Alex, okay, it asks for simplified radicals. Now the type of radical we are dealing with is a square root. And just kind of get things started off. Okay, so for the perfect squares, okay, so you have with the natural numbers or the positive counting numbers. Okay, so you have 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, and I can go on continuously. Okay. But now for the all intents and purposes, now if I reduce the square root of 48, 48 is not among the perfect square numbers. Okay. However, it is the multiple of a perfect square greater than 1. And you could factor out 48 from 4, or you could take 16 and just a little quicker route. You have the square root of 48, and the highest perfect square divisible into 48 is going to be 16. So you have 16 times 3. And for the square root of 48, you have the square root of 16 times the square root of 3. And square root of 16 is 4, and we have times the square root of 3. And let me mention this in case, what if I had factored out 4 instead of 16? Well, it's a little bit longer a pathway, but so you have like the square root of 4 times 12. And guess what? 12, not a perfect square number, but it is still a multiple of a perfect square greater than 1. So you have like 12 factors out to 4 times 3. So like the square root of 4 times the square root of 4 times the square root of 3. Square root of 4 is 2. Square root of 4 is 2. And times the square root of 3. And so you still come out to 4 times the square root of 3. All right. So just going back to what we have in the original problem, we have x is equal to plus or minus the square root of 48, again, which in reduced radical terms becomes plus or minus 4 times the square root of 3. And you can separate the terms, whereupon we have 4 times the square root of 3, as well as its additive inverse, which we have as minus 4 times the square root of 3. Now, and going back to the problem sets, okay, and we had a couple of items, okay, and it was just asking for the approach, that is the square root property of equality, okay, as the method to solve what we have in numbers 40 and 41, and for what we have, just referencing what we have in the exercise set. So we have with the case that we have in number 40, so we have 6v squared minus 30 is equal to 0. Now for this equation, now you could factor out 6, you could divide the equation by 6 right away, or you can do it later. Now for 6v squared minus 30 is equal to 0, let's say that if I just go ahead and isolate the v squared term by adding 30 to both sides. This is one approach, not the only approach, with just one pathway created. So we have 6v squared is equal to 30. And if I express in terms of v squared, so we have with division by 6, so I have 6v squared over 6, this will become v squared. 30 over 6 is 5. And just like what we have with x squared, we're going to have with v squared. And your p-value is going to be at 5. So if we go from v squared to v, we're going to have plus or minus, okay, the square root of 5. And just separating the solutions, we're going to have the negative of the square root of 5 as well as the positive square root of 5. In the case what we have with 41, okay, this time we're going from x to v to now looking at solving for the letter k. And in this one, okay, if we're looking at, once again, utilizing the square root property of equality, okay, so you have k plus 2 quantity squared is equal to 28. Okay. All right. And again, just taking what we have here, so you have like k plus 2 quantity squared is equal to 28 represents x squared is equal to p. And if I go from x squared to x is equal to plus or minus the square root of p. Now for what I have in the equivalent for this equation, so I'm going from k plus 2 squared to k plus 2 . Okay, so I have plus or minus, okay, the square root of 28. And just like the earlier case where we have with the number 48, I have the same situation with 28. 28 is not a perfect square number, but it is the kind of number that does have a perfect square greater than 1 that would be divisible into it. So we have, in the case of the square root of 28, now the highest perfect square that is divisible into 28 is going to be 4. So you have the square root of 4 times the square root of 7. And so you have 2 times, okay, the square root of 7. So for the square root of 28, you have 2 times, okay, the square root of 7. All right. And in compact notation terms, okay, now again, just like earlier in the earlier example, okay, it had a binomial with x plus 1 has set equal to plus or minus the square root of 37. And whatever methodology I use to undo the constant, I want the created constant to be in front of the plus or minus irrational root combination. Okay, so we have with k plus 2 equal to plus or minus 2 times the square root of 7. So we have k plus 2 minus 2 again, so we have minus 2 situated in front of plus or minus 2 times the square root of 7. So we have here, we have k is equal to negative 2 plus or minus 2 times the square root of 7. And just drawing out the separate terms. So I have negative 2 plus 2 times the square root of 7, as well as negative 2 minus 2 times the square root of 7. Okay, so with quadratic equations, again, there are various ways of solving. Again, we have just given the right coefficients, okay, we have the zero product property is a potential option, and also we have the square root property of equality, also an option, and where you might have other quadratic equations that might be maybe not as intuitive to solve, like in terms like, okay, say that the trinomial might be factorable, but in terms of factoring, it might not be an easy process. Like especially if you have a something like 2x squared plus, let's say 14x plus 19. Okay, maybe factorable, may not be. That one would not be. But if you're still looking for the solutions, there is yet another item in the arsenal that you can add. Okay, if the zero product property is not obvious and the square root property of equality is not quite so obvious, and we have with this other measure, okay, and this will be that which we have derived from a quadratic equation in its standard form. Okay, so we have so we have with the quadratic equation in standard form, again we have ax squared plus bx plus c is equal to 0, whereupon a does not equal to 0. And now, in terms of solving for x in this one, the derivation is a rather long process, and it would involve stuff like what would be referred to as the completion of the square. And this would be, and we'll be looking at stuff like this once you get into the quadratic functions, like what we have with the vertex form. But from the quadratic equation, what would happen here is that the solution combination we would have in x, this would be what we have in the quadratic formula. So we would have the x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a, whereupon a does not equal to 0 once again. And now for what we have in the case of solving by the quadratic formula, okay, and we'll just say that we have among our cases, and let's say okay, so we're looking at solving by quadratic formula use. Now, let me mention about the quadratic formula. Many will get right away what represents negative b as well as 2a and b squared. I would say that the most common misstep will be the minus 4ac portion. Now, that negative 4 is already baked in, but it's like in terms of how the a and the c are applied in this particular part that some ends up subtracting when they mean to add, and vice versa. So be careful with the sign value that results from multiplying negative 4 as well as when multiplied by both a and c. And let's say that for what we have as first case, we can say we have 2x squared plus 7x plus 1 is equal to 0. Now this type of trinomial, okay, now from this standard quadratic equation, okay, now you might be thinking of utilizing, okay, factoring by grouping, okay, but I will mention if you multiply 2 and 1, you have 2 times 1 is 2, and now if you notice, okay, we have factors of 2, and you'll be trying to find those that will add up to 7, but the thing is that for the integer factors of 2, you have 2 and 1, -2, -1, and the sums will be respectively 3 and -3, but not 7. So we cannot factor it in terms of integer coefficients. So this is where the quadratic formula can become of use. So we have a 2x squared. Okay, so a is represented by 2. For 7x, we have b at 7. And for c, since we have 1 added, c is going to be at positive 1. And for what we have for x, okay, so you have negative b plus or minus the square root of b squared minus 4ac all over 2a. And so we have with negative b, okay, so I have negative 7 plus or minus, okay, the square root, okay, so we have for b squared, again, b is at 7, so I'm going to square 7, and I got minus 4 times 2 from a, and we have times c, which we have at 1. So I have negative 7 plus or minus. And if I get too far ahead, I have to identify 2 times 8. Okay, so you have 2 times 8, so you have 2 times 2. Okay, so this is what we have upon substitution. Okay, so we have negative 7 plus or minus, okay, the square root. Now 7 squared is at 49. For minus 4ac, so I have minus 4 times 2 is negative 8. Negative 8 times 1 is still minus 8. And we have all over 2 times 2, which is going to be at 4. So you have negative 7 plus or minus, okay, the square root of 41. Now 41 is a prime number. Okay, so unlike, say, 48 from earlier, as well as 28, this is a kind of radical that cannot be reduced. And just drawing the solutions separately. So we have negative 7 plus the square root of 41 all over 4. And we have negative 7 minus the square root of 41 also over 4. Okay, now, and let's say that as another case, and say if we have very similar to this problem, at least in terms of the appearance. Okay, and let's say that just kind of a slight modification. We adjust the middle term. Say if I have 2x squared minus 7x plus 1 is equal to 0. Now again, we cannot factor this trinomial into integer coefficients. Okay. Now this time we have a still equal to 2, and because the middle term is minus 7x, and since bx is represented by minus 7x, your b value is now at negative 7. And since we have plus 1 at the end of the trinomial, okay, we still have that c is equal to 1. And now just taking what we have and again just reapplying the quadratic formula. So we have for, once again, just applying the substitution. So we have negative b. Okay, so that's going to be the negative of b. And b is already at negative 7. So I'm going to be taking the opposite sign of negative 7. And I have plus or minus, okay, the square root. And for b squared minus 4ac, so b squared. So I'm looking at the square of negative 7. And we got minus 4 times 2 times 1. We have all over 2a, again, which is going to be 2 times 2. Now again, compared to the earlier example, okay, the only change really is with b at negative 7 as opposed to positive 7. Okay, so for negative b, we have the opposite sign of negative 7, so this would be a positive 7. And the square of negative 7, or negative 7 times itself, we still have at 49. And we have negative 4ac, so it's negative 4 times 2 is negative 8, times 1 is still minus 8. We have all over 4. And for the compact solution combination, we want to have positive 7 at the front, plus or minus the square root of 41 all over 4. And again, just itemizing, so we're going to have 7 plus the square root of 41 all over 4, as well as 7 minus the square root of 41 also all over 4. Okay, and to what? Just in the case of solving by the quadratic formula, okay, and just for the next few moments, let's see what we get in the case of 2x squared minus 9x minus 1 is equal to 0. Okay, for this particular problem, again, just like the two earlier cases, right, we have a quadratic equation that is in standard form, but the trinomial, okay, is not factorable into integer coefficients. So just taking what we have in the setup, okay, so we have a 2x squared minus 9x minus 1, and let me make this view a bit larger. Okay, so we have a 2x squared minus 9x minus 1 equal to 0. So again, we have with the quadratic formula set up, so we have with a, okay, so we have a is equal to 2. And since we have the subtraction of 9x, okay, b is at negative 9. And for c, okay, so we have c is equal to negative 1. And just looking at what we have at the substitution stage. So we have negative b plus or minus, okay, the square root of b squared minus 4ac all over 2a. And we have with direct substitution, so we have negative b, so this will be the opposite sign of negative 9. And we have plus or minus, okay, the square root. Okay, so b squared, we have the square of negative 9. And for minus 4ac, so we have minus 4. Then we have times 2 times negative 1. And we have all over 2a, so this will be 2 times 2. And after the substituting, okay, so we have the opposite sign of negative 9, so this will be a positive 9. And we have plus or minus, okay, the square roots. Now negative 9 squared, that is going to be 81. Now for the minus 4ac parts, okay, and looking at what we have for a and c, okay, this particular portion translates out to where we have negative 4 times 2 is negative 8. And then in turn, negative 8 times negative 1 becomes positive 8. And then we have in the denominator, okay, so we have it 4. And so we have with the solutions, we have 9 plus and 9 minus the square root of 89 all over 4. And 89, just kind of like what we had with 41, that is another prime number. So this is a radical that not only has a value that is not a perfect square, but it is also a radical with its value cannot be reduced to a lower radical. Okay, so you have, in this case, you have 9 plus the square root of 89 all over 4. And we have at the lower end, we have 9 minus the square root of 89 all over 4. And for what we have in the text, okay, that we have regarding utilization of, okay, the quadratic formula, and now we have a change in the variable, and from the problem set that we have here for number 64. We're looking at the variable n. So you have n squared plus 8n, okay, is equal to negative 3. And so we have a quadratic equation that is not yet in standard form. And just moving the minus 3 over by adding, so we have n squared plus 8n plus 3 is equal to 0. Okay, and the n squared, since we're going to be drawing out the coefficients representing a, b, and c, and also since we have a trinomial that cannot be factored into integer coefficients, okay, so you have a positive 1n squared. So we have a equal to 1, and we have b equal to 8, and c equal to 3. Now, again, we're solving for n as opposed to x, but we're still going upon the same premises in the quadratic formula setup. So we still have negative b plus or minus, okay, the square root of b squared minus 4ac and we have all over 2a. And so looking at what we have and substituting, so for negative b, so you have negative 8, you have plus or minus the square root. Now for b squared, okay, this is going to be 8 squared. And we have minus 4ac, so you have negative 4 times 1 times 3. And we have all over 2a. So you have 2 times 1 And okay, so for the b squared minus 4ac portion, now h squared is at 64 for minus 4ac, so I have negative 4 times 1 is negative 4 times 3 is negative 12. So we have negative 8 plus or minus, okay, the square root of 52. And once again, the denominator is going to be at 2. Now, unlike 41 and 89 just a moment ago, okay, 52, in spite of not being a perfect square number, it is nonetheless the multiple of a perfect square that is greater than 1. So I can reduce this particular radical, sort of like what I had with, in the case of 48 as well as 28. So we have with 52, okay, the highest perfect square that will go into this is going to be 4. And so for the square root of 52, this will come out to the square root of 4, which is 2 times, okay, the square root of 13. So we have, in the case putting back we got negative 8 plus or minus 2 times the square root of 13 all over 2. And if you notice, we have even valued leading coefficients. Okay, so you have negative 8, which is even, and in front of the square root of 13 we have 2, which is even, and the denominator is also even. And I can simplify this, and I'm just going to take these terms apart. So we have negative 8 halves plus or minus 2 times the square root of 13 all over 2. Now for what we have in terms of the compact display of what we have here, so negative 8 halves, this will go to negative 4. We've got plus or minus. Now for 2 times the square root of 13 over 2, we just have the 2's to go out. So this particular second half of the ratio combination, this goes to the square root of 13. So we have with our irrational roots, okay, we have for the combinations, we're going to have negative 4 plus the square root of 13 and also negative 4 minus the square root of 13. All right. Okay, now sort of tying in together items we've looked into and just crossing over into the realm of and we'll say that we have equations with rational expressions. And say if we're looking at solving for x, and we'll say that we have say for our first case, okay, where we're going to have a quadratic equation, and this one is actually pulled out from number 60 in your textbook, whereupon we have 1/3 of x squared minus 7/6 is equal to 3 halves of x. Okay, now we have a quadratic equation, and you could write this equation, move the 3/2 x in the middle, and have this set up in standard form. Okay, and you would have a standard form equation with fractional coefficients. But let's say that if you want to undo the presence of fractions, since we're dealing with an equation and we're trying to solve for x, okay, what you can do is that you can just make the coefficients into whole numbers, and we can do this by multiplying everything out by the least common denominator. And the smallest value that all of 2, 3, and 6 will go into is just going to be at 6. So if I make the adjustments here, so you have 6 times 1/3 of x squared, and so you have minus 6 times 7/6 is equal to 6 times, okay, 3/2 of x. And if you already see the coefficients, that's fine. And just carrying this out a little bit further. So you have 6/3 of x squared, and like you have minus 6 times 7 is 42 over 6. We have is equal to 6 times 3 is 18 over 2, and we have times x. Again, so like 3 will go into 6 2 times, and then we have 2x squared. Over here you can have like 6 going to negative 6 negative 1 time, and then we have over 7, or again negative 42 6, which is still negative 7. And we have 18/2 of x, so this will be 9x. And just taking what we have and arranging where we're going to have the quadratic equation in standard form. So I can just move the 9x over by subtracting. So we're going to have 2x squared minus 9x minus 7 is equal to 0. And for what we have in this particular setup, again, we have quadratic equation where the trinomial cannot be factored into integer coefficients. So in terms of determining the solution, again, we can revert to the use of the quadratic formula. So we have the a is equal to 2, b is equal to negative 9, and c is equal to negative 7. And we have with the quadratic formula, so x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And we have with direct substitution. Okay, so for negative b, so you have the negative of negative 9, plus or minus. Okay, we have the square root. Now for b squared, okay, we have the square of negative 9 minus 4ac, so you have minus 4 times 2 times negative 7. Again, we have all over 2a, so we have it 2 times 2. And so we're going to have here, okay, negative b, have the negative of negative 9, so this will be a positive 9. And we have plus or minus, okay, the square root. So you have the square of negative 9 is going to be 81. And again, be careful with that which represents minus 4ac. So working, we have negative 4 times 2 is negative 8 in turn, negative 8 times negative 7 comes out to a positive 56. Again, we have 2 times 2 is 4. So here we're going to have 9 plus or minus the square root of 137 all over 4. And 137 is a prime number, and we have the square root of 137 cannot be a reduced radical. So we have in the combination, we're going to have 9 plus the square root of 137 all over 4. And for the smaller result, we have 9 minus the square root of 137 also over 4. Now, from the other day, okay, there were a couple of exercises we looked at where we looked at simplifying ratios and identifying the restricted values. And let me give you a situation where you would have restrictions. And we will say that for this second case, let's say if we have, and this one's going to be sort of drawn out, but I just wanted to mention, say if you have something like 3 plus plus 4 all over x plus 1 is equal to 5 over x. Okay, notice you have the x terms or expressions are in the denominator. Let me mention some things here. Now, whatever we have for x, again, like restricted values will be those values that are not allowed because they would set the denominator equal to 0. So you have like x plus 1 cannot be 0. So in this case, x cannot be negative 1. If I have negative 1 plus 1, I have the 0 denominator. And for 5 over x, okay, we have the x cannot be equal to 0. So we have a bit of a twofold restriction. So you have the x cannot be negative 1. No, so x cannot be 0. And also sort of tying in, okay, we have, again, just like earlier, clearing out fractions. Now the denominators, again, we have x plus 1 and x. And I can set things up and just clear out the fractions. If I multiply the terms throughout by the least common denominator, which would be x times the quantity of x plus 1. Okay. So multiplying by the least common denominator. Again, I've been asked, okay, when do you write the fractions in terms of the LCD, and when do you clear out the fractions multiplying by the least common denominator? You clear out whenever you have an equation. Okay, but if you just looked at combining terms, like I would write 3 as a fraction with x and x plus 1 on the bottom. But since I'm looking at solving an equation, I'm looking at removing any denominators. Okay, so we have for 3. So I have 3 times x times the quantity of x plus 1 as for 4 over x plus 1. Again, we have multiplying, so we have x times the quantity of x plus 1 again, we have equal to 5 over x. Again, we have times x times the quantity of x plus 1 So just looking at what we have in the process. So just having duplicated. Now we have 4 over x plus 1. Now the x plus 1s will go out. For the last ratio, we're going to have x to go out. And looking at what we have left standing. So you got 3x times the quantity of x plus 1. So you have 3x squared plus 3x. For the next set of terms, so you have x plus 1 to cancel, but we have 4 times x. And to the right, now we have x's to cancel, but we have the distribution of 5 over the quantity of x plus 1. So this will become 5x plus 5. Okay. So in working with what we have now, we got 3x squared plus, and we have 3x plus 4x will make 7x is equal to 5x plus 5. And we have the establishment of a quadratic equation. And if I rewrite this in standard form, okay, so I have 3x squared is the highest order term, and it's located on the left. And what I can do here is we can take the terms from the right and remove. Okay, so I can take out 5x. And also subtract 5. So you're going to have in this particular layout, okay, so you're going to have 3x squared, 7x minus 5x, okay, so this will yield 2x. And we have minus 5, okay, is equal to 0. Now, we have, for this trinomial, you could use the quadratic formula as one approach. But this one also happens to be factorable. And so it's a little bit drawn out, but I think what I'm going to do here is that for 3x squared plus 2x minus 5, I'm going to factor this one. So just kind of stepping to the side here. So you have a 3x squared plus 2x minus 5. If I take the first and the last coefficients, so I have 3 times negative 5 is equal to negative 15. And what I want here will be factors of negative 15 whose sum will be positive 2 as signaled by plus 2x. But right now we have, earlier we formed negative 15 upon multiplying 3 and negative 5. However, even though 3 times negative 5 is negative 15, 3 plus negative 5 is a negative 2 as opposed to a positive 2. But I can rectify this for if I just change the signs, make this 3 a negative and the negative 5 positive. Negative 3 times 5 is still negative 15, and combining in terms of adding, negative 3 plus 5 comes out to positive 2. So we're going to have here in the rewrite. So again, we have 3x squared plus 2x minus 5. And if I take the coefficients negative 3 and 5 and form x terms upon splitting 2x, okay, so we have 3x squared minus 3x, and we have plus 5x minus 5, and crossing over to what we have in the grouping. So we have the quantity of 3x squared minus 3x. And we have the middle operation to be addition. That was why we have to separate the first and second terms apart from the third and fourth. Okay, so we have plus the quantity of 5x minus 5. And drawing out the greatest common factors from the pairings. Okay, so with 3x squared minus 3x, the greatest common factor is going to be at 3x. And into 3x squared minus 3x, so this will be the quantity of x minus 1. And we have plus, and for 5x minus 5, okay, greatest common factor is going to be at 5. And 5 goes into 5x minus 5, x minus 1 times. And so we have with the factors here, we have x minus 1 shared in common. And the other factor will arise from combining the outside terms and operation. And those outside terms being the respective greatest common factors and the addition that unites those terms. Okay. So, and taking what we have now back into the equation. So for 3x squared plus 2x minus 5 is equal to 0, if I take these factors, okay, so I have the quantity of x minus 1 times that of 3x plus 5 is equal to 0. And now for the setup upon utilizing the zero product property, okay, we have x minus 1 equal to 0, as well as setting 3x plus 5 equal to 0, and for x minus 1 equal to 0, so if I add 1 to both sides, we're going to have that x is equal to 1, and for 3x plus 5 equal to 0, if I subtract 5, we're going to have that 3x is equal to negative 5, and we have with division by 3. With division by 3, okay, we're going to have an apparent non-integer solution with x at negative 5/3. Okay, so for what we're going to have in this case, right, so we're going to have x equal to 1 and x equal to negative 5/3. Okay, and I was a little bit quick in asserting these as being the solutions, but let me just kind of backtrack. Say have x at 1, x at negative 5/3, and again the restrictions were that x could not be negative 1 or 0. Okay, so as long as you have done the algebra correctly and the resulting x values happen to not be negative 1 or 0, then those values check out. But if I had like negative 1 and 0 for my apparent solutions, then this equation would have had no solutions. But in this particular case, the values of minus 5/3 as well as 1 satisfied the restrictions that x could not be 0 or negative 1, and so that wound up working out. Okay, all right, and okay, gotcha. Okay, and okay. Now, just kind of a quick item, I just want to mention now for equations, okay, that consist of fractions, and there is one more category. Okay, and this will be a much simpler process than what we just encountered. Okay. And in the case of proportions, for what we have in proportions, okay, and you would have like a statement of equality between ratios. See, if I could have if A over B is equal to C over D. Then you're going to have what will be referred to as proportional cross products. In other words, we have A is going to be mapped with D, and B is going to be mapped with C, such that the proportional cross products, which will be A times D, is going to be equal to B times C. And this will be on the conditions that our original denominators are non-zero in value. Okay, so you have that such that B does not equal to 0, and that D is also not equal to 0. And let's say that if we have, as an instance, okay, and in the case of taking what we have and solving for proportions, and my light went out. Okay, and let's say if we have just an example case. If you're looking at solving for x, okay, so we have, say we have a proportion. Okay, so you have 2 over x plus 4 is equal to 1 over x minus 3. Okay, and just to kind of mention, in case you have denominators at x plus 4 and x minus 3, so a bit of mentioning of the restrictions. Okay, so whatever we have for x, you cannot have 0 valued denominators. So if x plus 4 cannot be 0, x cannot be negative 4. And if x minus 3 cannot be 0, okay, so we have x cannot be at 3. And just to restate the restrictions. So the x cannot be negative 4, and x cannot be at 3. And so we have, I'm just going to just write this ratio set up again. So you have 2 over x plus 4 is equal to 1 over x minus 3. So in terms of taking what we have and just sort of mapping together, so you have 2 and x minus 3. As well as x plus 4 and 1. So just taking proportional cross products. Okay, so you have A times D, B times C, and it doesn't matter what order you place the factors. It could be x minus 3 times 2, 1 times x plus 4, regardless. Okay, so you have, if you multiply 2 and x minus 3, so it's going to be 2x minus 6. And for 1 times x plus 4, or x plus 4 times 1, we have x plus 4. So we have like terms on opposite sides, just like the very first problems that we started out with. So I can combine the x terms, and I'll take out the smaller. So we have here 2x minus x becomes x. And we have x minus 6, okay, is equal to 4. And we have just with the two-step equation we started out with. Okay, so we have just, in the case of isolating x, okay, so I can now add 6 to both sides, and so it's going to turn out that for x is equal to 4 plus 6, okay, which is going to be equal to 10. And so just looking at this apparent solution, so whenever I was looking at solving for x, again, whatever I have for x cannot have any denominator equal to 0. So we have x at 10, and the restrictions Again, we have that x cannot be -4 or +3. So 10 checks out. And that is going to be the solution. Okay, and in a sense, you can sort of check the results, see how the fractions compare. So you have like 1 over 10 minus 3 is 1/7. And for 2 over 10 plus 4, that's going to be 2/14, which is also reducible to 1/7. All right, and now just some items to go ahead and be looking into. And again, your Alex homework set, okay, that is due Tuesday night, and that again is already up. And now just items to go ahead and be looking at from the textbook. Okay, we have from page 69. Okay, so you have numbers 68, 74, and also numbers 80 through 82.